So this is the second video on the binomial distribution. Now in the first video I've covered what the binomial distribution means, what it means for a random variable to be distributed with the binomial theorem, and all we haven't covered is how to use this formula, okay? So if you don't quite understand why we might want to use this formula or not, then go back to the other video and have a look at that. All I'm going to do here is tell you what this formula means, why it fits binomial distribution, and how to calculate with it. So, first of all, if I've got a binomial distribution and I've got a question like this, what's the probability that x, and remember x is distributed with a binomial distribution n and p, what's the probability that random variable takes a value 6? So that's saying I'm doing n trials, probability of success at each trial is p, and what's the probability of getting 6 successes? So if I flip the coin 10 times, what's the probability of getting 6 heads? That sort of thing, okay? Now, this formula tells us that that probability is n choose 6, which we can write as nc6 or as n6 in a set of brackets so it looks like a vector. I'm going to go for this notation just because I prefer it. Then it's p to the power of 6, 1 minus p to the power of n minus 6, okay? So that's the first thing, is that the little r in this formula is we're interested in what's the probability of getting that many successes, okay? If I knew how many times I'd flipped the coin, how many trials I've done, that would be n, and then p is the probability of success. So if I take the example that I first started talking about in the last video, I'm flipping a coin 10 times, the probability of getting a heads on that coin is 0.2. Then I'd say x is distributed with a binomial distribution 10, 0.2. What's the probability of getting 6 heads on that particular coin if I flipped it 6 times? Well, that is 10, choose 6, 0.2 to the power of 6, 0.8 to the power of 4, okay? So, where does that come from? Well, if we flip the coin 10 times, we could record the results. We could have heads, tails, heads, heads, tails, heads. We get a string like that, which would be 10 items long, wouldn't it? We'd have heads and tails written down 10 times in a row. If I've got 6 of them, 6 of these little trials turned out to have a heads, then out of these 10 slots, you can imagine it as 10 options, right? There's the result of the first flip, the result of the second flip, the result of the third flip, the result of the fourth flip, and so on. So the first one came up heads, the next one came up heads, the next one came up tails, heads, tails, tails, whatever it is. But we know that out of the 10 sort of slots to be filled, the 10 results of the experiment, 6 of them turned out to be heads. And obviously then 4 of them turned out to be tails. What's the probability of getting head? Well, we said that was 0.2. What's the probability of getting a tails? We said, well, if the probability of getting heads is 0.2, probability of getting tails is 0.8, okay? So if I've got 6 H's and 4 T's, the probability of that is 0.2 to the power of 6, 0.8 to the power of 4, because each trial is independent. If trials are independent, the probability of getting a head and a head and a tail and a head, we just times those things together because we know that each trial is independent. That it has to be, because that's one of the criteria for having a binomial distribution. So 0.2 to the power of 6, 0.8 to the power of 4, and that is the probability of getting this particular string of heads and tails. So success, however many times you got success. Failure, well, if probability of success is 0.2, probability of failure is 0.8. If probability of success is p, probability of failure is 1 minus p, because at each trial we can only have success or failure. So those two numbers have to add up to 1. So success, 6 times, failure, the rest of the time, so n minus 6, okay? Success, 6 times, failure, 4 times, and I did 10 trials, okay? Now, that's the probability of getting that particular outcome. If you like, it might help to picture it like this. We've got a tree diagram. We can get heads and tails first. The next one we can get heads or tails, but this isn't just a small tree diagram, this goes on. There are 10 iterations of this tree diagram, so that's the first flip, the second flip, the third flip, the fourth flip, the fifth flip, and you can imagine the branches branching out and branching out and branching out and branching out until the end of it. There's loads and loads of branches here. Now, what we've done is we've found one particular branch, one particular way through this tree diagram where there are 6 heads and 4 tails. But what I want to know is all the ways through this tree diagram where there are 6 heads and 4 tails. Okay. Now, any individual path through the tree diagram, 6 heads and 4 tails, has got the probability of getting that particular branch is that. All I need to do then is find out how many branches there are with 6 heads and 4 tails. That's the same as saying, okay, you've got 10 spaces in a row, or n spaces in a row. You're going to fill 6 of them with h's and the rest of them with t's. Now that is the number 10 choose 6. Okay? Or to generalize this, if we've got n spaces, and I'm going to pick r of those to fill with a success, then there are n choose r different ways of doing that. Okay? So, for example, I could put all the heads first, 1, 2, 3, 4, 5, 6 heads, and then 4 tails. Or I could have 1 head at the start, and then the other 5 over here at the end, and then the tails in the middle. Or I could have heads, tails, heads, 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 tails. You know, you can imagine all the different strings of heads and tails. The number of different ways of getting 10 slots and filling 6 of them with h's, leaving the rest of them to be filled with t's, is called 10 choose 6. That's what that number is. Now, the question then is, well, how do I calculate that number? The quick answer is there is a button on your calculator that will do it for you. There is a way of doing it without the calculator, and you are expected to know the way of doing it without a calculator. But there is a button on the calculator that will do it for you. So what I'll do is, for this video, we'll just concentrate on being able to do this with a calculator. The next video, we'll look at how to do this without a calculator, and we'll look at where that number comes from, for those of you that are interested. So, let's take example 4. X is distributed with a binomial distribution 12, 1/6. That means I'm doing 12 trials. I'm saying how many successful trials did I get if the probability of success at each trial is 1/6. So I'm flipping a coin 12 times. The probability of getting a heads on this coin is 1/6. How many heads? Well, what's the probability of getting 2 heads? What's the probability of the outcome of that random variable being 2? So that will be, well, that means I've got a 6th has happened twice. That means failure with a probability of 5/6 happened the rest of the time, so that must be 10. And that is 12 choose 2 different options there. Okay, so 12 choose 2, 1/6 squared, 5/6 to the power of 10. And then I calculate that. Now, this little bit here in the textbook I'd say is a bit misleading. What I'd say is put that number in your calculator, and then obviously put these numbers in your calculator as well, but my point is to use the special calculator function for that. Put that in your calculator, and then what you end up with is 0.296, okay? Now, it's never a good idea to be just putting something in your calculator and sort of doing it blind. From there, it's not obvious at all what sort of number would come out of the calculator. Okay, we know it's going to be a probability, so something between 0 and 1, but we'd be expecting something like 0.001 or 0.9, or, you know, we don't know how big the number should be. So it is vital that we get an understanding of how to calculate this without a calculator. Like I say, we'll do that in the next video. Same thing here, probability of x equaling 0.9 is the same as saying what's the probability of getting 9 successes? Well, it's 12 choose 9, 1/6 to the power of 9, 5/6 to the power of 3. That is 9 successes, 3 failures, okay? A lot of people tell me this formula is difficult to memorize, but if you think about it that way, probability of the random variable taking the value r is the same as saying what's the probability of having r successes. Probability of success is p, so p to the power of r, 1 minus p is the probability of failure, and that happens the rest of the time, i.e. n minus r. Okay? So, if you don't mind using a calculator, and by the way, you should mind using a calculator all the time, you won't need to be able to do these without a calculator and get an idea of how big the numbers should be. But if you use a calculator for all the questions, you should now be able to do exercise 6b. For the next video, we will look at where n choose r comes from and how to calculate it without a calculator.